In this problem, we're giving data at one pressure and temperature. So we're given a mole fraction in liquid phase, the mole fraction in vapor phase for a binary system in vapor-liquid equilibrium. And then the question is, at this temperature, is there some composition where this system has an azeotrope? And then if so, what's that composition? If not, justify why there's no azeotrope. And to model the non-ideal liquid phase behavior, since we're assuming the gas phase is an ideal gas, to model the liquid phase behavior, we'll use a one-parameter model. And so the idea behind this is we're starting out the system where we have measurement at one condition. And let me make a simple drawing. Here we're showing the two data points where we have measurements, and the question is then, if I draw vapor-liquid equilibrium lines, I'm now asking, does this go up through a maximum, or does it connect where this is P1 set and this is P2 set, or does it not have a maximum at this temperature? First thing we want to do is use the data we have to determine this parameter. And then once we have that parameter, we can look at other conditions using the same parameter to get activity coefficients and determine the presence of an azeotrope or not. Let's look at the case. Starting conditions x1, gamma 1, P1 set, where gamma 1 is the activity coefficient, mole fraction of vapor phase, total pressure. We're given all the information. I can calculate gamma 1. So let me pause. So this shows the value of gamma 1. For the one parameter model, the log of gamma 1 is related to mole fraction component 2 and the parameter b. And that means now I can calculate b by making this substitution. And when I make this and calculate the log, I can solve for b. And so this is the b now I'm going to use at the other condition. And that condition is where we have an azeotrope. So let's now say at some other point, we're interested in whether this point exists. Of course, that point, azeotrope means x1 equals y1. So let me write the modified Raoult's law expression again. x1, gamma 1, p1 set equals y1p. But now I'm interested in, do we have a point where x1 equals y1? So if I look at this expression, of course, x1 equals y1 means these cancel from the expression. Then when I rewrite this, and what I'm going to do is substitute for gamma 1. So gamma 1 from here is an exponential of b times x2 squared. So e to the b x2 squared is gamma 1. P1 set's a number that we know. P is the pressure at the azeotrope, and we don't know that. And of course, we likewise can write x2 gamma 2 P2 set equals y2p. And then we can make the same at the azeotrope, and we make the same type substitution. So now I have two equations and three unknowns, namely pressure, x1 and x2, but of course x1 plus x2 equals 1. So that's the third equation. So I'm trying to determine if there is an x1 where x1 equals y1. And so I'm going to eliminate pressure in order to solve these equations. So the left side of these two equations would then be equal to each other. And then I can simplify that. So let me pause and do that. So I've simplified over here, and now I can make the substitution for B and the saturation pressures. Let me also make a simplification that'll just make the manipulations a little easier. So x2 squared minus x1 squared can be written as a product x2 minus x1, x1 plus x2. And of course, x1 plus x2, this is equal to 1. And so this means this is just x2 minus x1. But I can write this in terms of x1, since x2 is 1 minus x1 minus x1. So this is 1 minus 2x1. Now I'll substitute back into expression for b. So I'm just going to simplify and solve for x1, this equation. So we have a solution to the equation when we said x1 equals y1. And so this means, and of course this would be y1. This is the point where we have an azeotrope. And then we can go back to the equations, and let's look at, for example, this equation, or of course this one, if we want to write it in terms of x1 or x2, we can calculate the pressure. So let's do that. So I'll make the substitution, we get a pressure. So this pressure at the azeotrope is greater than, so the pressure is greater than P1 sat, but only slightly. So it's a very shallow maximum, but indeed is a maximum. And we've answered the question of system using this simple one parameter model, we would predict an azeotrope.